By now you're familiar with Kinetics core shell technology, so you know the columns deliver ultra-high performance on conventional HPLCs such as this Agilent 1100. So today, we will show you how just a few simple modifications can help maximize the performance of your Kinetics core shell column. The good news? It's easy. Dr. Rustamov.
Hello, I'm Dr. Ismail Rustamov, R&D group leader here at Vinaquips. The most relevant system parameters affecting the peak volumes are the following: the connective tubing volume, detect response time, and flow cell volume.
Now with Dr. Rustamov's supervision, I'll now demonstrate the optimization steps for you.
You must minimize system volume using smaller diameter connective tubing. Tubing may run from the auto sampler to a column heater and finally to the detector. I will also have you change the injector needle seat to a lower volume model. I call these changes Phase 1. They are easy, inexpensive system improvements for Kinetics core shell.
Okay, phase 1, here we go. It appears that the tubing runs from the auto sampler to a Vinaquips Synergy 6-column switching valve, then to the detector. Let me get started disconnecting the column and the connective tubing. Removing the door, you can then unscrew from the auto sampler, then from the detector. Nice and easy.
Now, replace the tubing you removed with lower volume red tubing. The 0.01-inch ID tubing has a solvent volume of 0.51 microliter per centimeter, adding a significant amount of dead volume to the HPLC system.
Small volume peaks in this tubing may dilute and become dispersed.
The smaller diameter red tubing has solvent volume of 0.13 microliter per centimeter and can maintain the peak integrity. Replace the conventional fitting with Vinaquips high-performance finger-tight fitting. Please make a good square cut. Bad cuts are a common cause of efficiency loss.
All right, now I'm going to reconnect the column to the auto sampler, bypass the heater, connect to the detector, and replace the auto sampler door.
Very good, Kevin. If your method requires temperature control, bypassing the heater is not required. Using the red tubing while having your column in the oven compartment will also provide you with noticeably improved results.
Sounds good.
The next thing you want to do to further reduce extra column bad broadening is to change the needle seat. You will need to go into the software to perform this.
I'm going to the diagnosis window of the software. Go to the High Performance ALS window, select Maintenance Positions, then hit the Start button in the sub-window titled Change Needle Seat.
This lifts the needle so that the seat can be replaced.
I'll remove the current needle seat and replace it with a low-volume part. Okay, I'm disconnecting the current needle seat. First, I'm removing the connection to the injector valve. And then with a gentle pry, I can remove the unit from the housing, with a spatula for instance. Now I can replace it with the low-volume needle seat. And reconnect the fitting. And then with a quarter turn at the end. There. Remember to come back to the software and end the program, or you will have some big problems.
Very good, Kevin. Let me show you how effective these simple phase 1 changes are on increasing system performance.
Okay.
First, before any changes were made to the system, I measured the efficiency of a neutral compound on 3 different Kinetics core shell columns, as well as a traditional fully porous particle type column.
Wow! Even without system optimization, the core shell columns show very high performance.
Next, I rerun the core shell columns after making the volume reduction just performed.
That's amazing! The efficiencies have really increased. These simple modifications have really made a difference.
And now let's go to Phase 2 system optimization. Phase 2 focuses upon simple detector improvements that allow the detector to perform at a higher level. First, you are going to change a software setting.
In the main instrument window, I'll select the Setup DAD signal option. Within that window, we'll want to change the peak width response time to the fastest acquisition rate possible.
This will vary depending upon the detector type.
In this case, we are increasing the response time from 2 seconds to 0.02 seconds, a 100-fold increase in data acquisition rate.
Then just hit OK, and you are done. This is a simple change. It was quick and costs nothing. Now, let's look at reducing more sources of post-column peak dispersion, specifically that which take place in a flow cell. Using Kinetics core shell columns, a peak's volume will be very small. Large flow cells will disperse narrow peaks and reduce the apparent efficiency of the column.
As a wide sample peak from a column moves through this flow cell, the volumes are nearly matched. Larger volume peaks don't appear to disperse in standard flow cells.
The high efficiency, low volume peak from Kinetics can be dispersed in a large volume of the flow cell.
Wow! Let's remove that large volume flow cell. I have the detector turned off, and I'm now going to disconnect the inlet and the outlet lines of the current flow cell. Once the lines are disconnected, removing the flow cell is really easy.
You will replace the large volume flow cell with a 3 mm flow cell. A smaller flow cell will maintain the integrity of the high efficiency Kinetics peak.
Gotcha. I'll put the newer, low volume flow cell into its position, and it snaps right in. Close the door. Then it's just a reconnection of the lines. And then with a quarter turn at the end. There.
And that is the end of phase 2. After the simple improvements, we see even greater gains in efficiencies on our core shell columns. The purpose of the phase 1 and 2 system improvements is to preserve the integrity of Kinetics peaks as they move through the connective tubing and the detector.
Amazing! With only these small changes, you can see that all 3 core shell columns are now producing efficiencies that are well within or above HPLC expectations. These dramatic increases in efficiency really do make a strong case for why labs everywhere should implement these simple system improvements.
You should also note that after these simple steps, there has been no improvement in the performance of the fully porous particle.
Yeah, that's a great point.
This is not surprising. The peak width eluting from the fully porous particle is already so very badly dispersed that even the non-modified system volume is not large enough to be additive.
And that's it. We've just optimized our system to maximize its performance for core shell HPLC columns. By combining core shell technology with these simple modifications, you too can have HPLC performance on an HPLC system.